Ground source heat pumps, variously known as geothermal heating or earth energy systems. There are two types of geothermal energy: high grade, which is the heat of the Earth's pressure turning water into steam, such as Old Faithful at Yellowstone National Park. Low grade geothermal energy is the heat within the Earth's crust. This heat is actually stored solar energy. This presentation deals with low-grade geothermal energy in the form of ground source heat pumps. A major advantage of a ground source heat pump is that it concentrates natural heat rather than using combustion, resulting in less carbon dioxide being released to the atmosphere. We'll discuss this more later. There are several configurations possible. Which you choose depends on several factors: the available space, design, materials, labor, maintenance, sizing, and of course, cost. Each configuration has its own unique characteristics and is suitable for different situations. Remember, a ground source heat pump uses the stored heat of the earth to heat your home. Shown on the right is a closed-loop vertical system. This configuration is good when you have limited yard space and in areas where trenching is impractical. It is more expensive to install, but requires less piping, as at the depth it is installed, the temperature is more stable. Less piping results in less transfer medium required. There are also several horizontal configurations available. In a series, it is easier to remove trapped air. There's a simplified flow path, and the heat transfer is higher per foot of pipe due to a larger diameter pipe being used. However, it requires more transfer medium, has a larger pressure drop through the piping, and longer trenches are required. When the loops are connected in parallel, you can use a smaller diameter pipe, less transfer medium, and shorter trenches. However, it is more difficult to remove air, and there can be difficulties in balancing the flow if all circuits are not equal lengths. A slinky collector is essentially a series configuration where the piping is looped. The trench length can be reduced by 65% compared to a conventional series connection, which reduces costs in trenching, but requires more piping per ton of heat exchange capacity. Other methods are less common due to their unique needs. On the left, the submerged. No trenching is required, but you must have a lake of sufficient depth. The loops are held by concrete weights at 6 to 8 feet below the surface, because at this depth it is not likely to freeze. If your lake is not a sufficient depth to ensure that it does not freeze during the winter, this is not an option for you. On the right is an open loop configuration. For this type, water must be plentiful and of good quality, non-corrosive and non-scaling, as the water is used directly in the heat exchanger. It is important to note that the water returning to the aquifer is the same as the water that was drawn from the aquifer. In open-loop configurations, groundwater is drawn up from the aquifer, goes through the heat exchanger, and is discharged to either a low-lying waterway, such as a pond or river, a dedicated drain field that has been properly sized for the drainage requirements, or it may be pumped directly back to the aquifer. This method has a higher heat exchange capability, but many other factors must also be considered, such as local laws and the quality of the water, as poor quality water can cause mineral deposits to form in the heat exchanger. Standing water deep wells are drilled directly into the bedrock to the aquifer. This type of ground source heat pump can be configured with one well or two, although some jurisdictions may require the second well, known as an injection well, for returning the water to the aquifer. Remember how I mentioned earlier that a ground source heat pump doesn't use combustion? This table illustrates just how much carbon dioxide you can keep out of our atmosphere by switching to a ground source heat pump. In some areas of the UK, coal is still used as a heat source. If someone using coal could switch to a ground source heat pump, they could save 7,500 to 11,600 kilograms of carbon dioxide per year. Even just switching from gas could save 2,000 to 3,000 kilograms per year. In addition to the environmental benefits and lowering your carbon footprint, many areas also offer financial incentives to switch to a ground source heat pump. Check with the authority having jurisdiction in your area and find out if a ground source heat pump is right for you.